Hello and welcome back to a new video. Now a bit different of a video. It's a post-contest analysis of some ACM problems we were solving on the first round on the Slovenian ACM. And we're going to take a look at all the problems, at their solutions, their intended solutions. The link will be in the description of this round. You can check out all of the problems, test cases, and solutions, and you can also probably submit the problems. I don't know if you can submit the problems if you're not like official with an official team account, but you may try. So okay, we're going to start from the simplest problem, and the problem with I think most teams solved is the scalar product problem. I'm just going to open up the problem. Don't worry that I will be translating all of that in English for you to see. It's just a simple problem. It's really not worth a lot of time. You are given some kind of vector, two vectors. One of the vectors you can't change, the other vector you can flip, you can swap any two adjacent entries in the other vector, or mirror the ith entry. What that means is just swapping the sign of the ith element. But when you first to observation to notice is swapping two adjacent elements can it can mean that like you can swap any two elements, not just two adjacent elements, because you can do this operation as many times as you like, and this operation as many times as you like, of course, in whatever order you want. But what the observation means is that not only that you can swap adjacent elements, you can swap any elements. And the solution is rather simple, and just sorting the two vectors by size, by size, and matching the smallest with the smallest element and the biggest with the biggest element. And if you need to flip the sign of the element in the second vector, you will do this, so everything is positive. This will get the maximum dot product of those two vectors. Yes, the maximum dot product of the ui, this initial u vector, and x, this new vector that you get. The solution, if we take a look at what we've posted, is just having like this massive like pair in structure, then sorting by the absolute value, sorting A by the absolute value, sorting B by the absolute value, of course. And then what you want is to have like some answer array and just match B and A. But if you need to, like, if A was negative, you put B negative. If not, you put it the other way around. And that is the solution, really. It's yeah. Nothing too complicated. Okay, let's get back. This is pretty straightforward problem. It's meant for all teams to solve. The next problem was this ships are sinking problem. So it's so this problem, you're given a matrix and you're given some you're given the size of the ship and how many of them are there of this size. And what you need to like notice that you can actually the sizes can repeat, doesn't actually matter, and the ships cannot touch, so like the ships cannot touch like this, and the ships can touch like this. there, and all of the ships must be horizontal and vertical, and yeah, it's a pretty just a problem just going to just checking out if the ships are good and counting how many of them are there. Ships are sinking. Yeah, just going through the matrix and brute forcefully just going through every ship. If you have visited, just checking if that ship is if there are no other ships that touches it. It's a I would say it's a okay problem, but I didn't like it. Okay. Another problem is this meeting rule problem. Oops, let's not show the solution before. If you want to solve all of the problems, I would suggest right now is the time to, because those two problems in a way everyone can solve. Right now is just the time to go and try yourself on the more complex problems. You've seen like till now the problems were easy. Now it becomes a bit more complex. Okay, this problem is not that complex. You're weirdly, I did not read this problem, but a colleague actually solved it on paper. I just wrote the solution. You're weirdly given some way of some like this, maybe. So you're weirdly, let me just take the pen here. You're given some intersections. Like you're given like a graph, but the graph is given pretty weirdly. It's just like which one of this is connected and which one of this is not connected. So some of them are like this. Let's say they are like this. Okay. Whatever. There is some like grid. And there is a starting point. There is like a current point. And there is an ending point. And what you can do is you always go for the, so from the starting point, we know that from the starting point, somehow the person came here. And then from the current point, we want to go to this point. But the problem is that, first of all, the person could have come from like from different directions. We don't know he came from here or from here. So we have to figure out from which direction the person came, and then from that direction, and then we know. So it's very important when you come from some other direction to some point. First of all, if you can go, there are rules in the BFS. So this is a rule-based BFS. If you can go in forward manner, you take the forward route. If you can't go the forward route, you try to take the right route. If there is no right route, if you can't take that right route, then you can go the left route. Otherwise, if there is forward or a right route, you can't go to the left route. Some rule like that. you can read the problem yourself, but what you need to know about these problems, where it is very important to know in which direction you came, or for every node you need to store for each direction some information. So we actually made like all of the arrays had the x and y coordinates and the direction coordinates as well. Say this is visited or whatever, because it's not the same when you come from one direction, and it's not the same when you come from the other direction. And the trick of this problem was, okay, you push first BFS from S to C. Even though you're on C, you need to know from which direction you came, from which direction it is the shortest path. Then you find out, let's say from this direction is the shortest path. I don't know, like let's say here, here, no, it will be like here, here, and here. Because if you go here, here, you will need like this. Okay, so like this one path, this is another. So let's say this is the shortest path. Now that we know that we came from this direction, we cannot go back from this direction. So we cannot go to the opposite direction. We cannot just switch. So we need to push BFS from each direction that is not this. Okay? And then when we push BFS, we need to find what is the shortest path to come to E. So it's just like double BFS, and you need to store information for for all of the 4 directions. The input is a bit more complicated. It's just like connect 0, 0 with 1, 0 and 0, 0 with 0, 1 on the matrix. So it's like you're already given these edges. Yeah, that's pretty much it about the problem. Let's see the solution. If you want to solve the problem, just pause and go solve the problem. We set up this connection network. This is just saying, okay, we can go. This is just adjacency. It's just a matrix, but it's not adjacent. Actually, it's a full-blown matrix. We say that the 0 is top direction, then the 1 is on the right, then 2 is on the bottom, and 3 is on the left, due to the fact that if you know this already, you can just modulo and shift the directions later in the BFS pretty easily. So from the starting point, we have the starting point, the current point, and the ending point. We want to find what is the direction that we've came to the current point. We clear everything out and we push BFS on it. If we've came to this point, we just take this direction. It's fine. Just clear BFS. Push now BFS from the current point to the ending point with this direction. So we've actually, okay, we've came from this direction. Now we're gonna push BFS from this direction onwards. And the answer, if the answer is -1, if we can't reach that point, then it's -1. If else, just answer this. Yeah, the BFS is just a simple BFS. Clearing is just clearing the visited. Simple BFS where you have, you just check if that point is the destination. If not, these are the rules. Now the rules can be more compacted, but with a lambda function or whatnot. But I just copy and paste it because, yeah, it's a contest. You have to be quick. You try first with this direction to continue in this direction. Then you try to turn right. So modulo 4 plus 1 modulo 4. Then if you can't continue on the straightforward, then you can only try to continue to the left. Okay, so and then we got to go to solve some of the other problems. So these three problems were left. Now I will say how are they. So this next hard problem is this here, and this problem, Feudal Lords. It's on English, okay. Feudal Lords. You're given a tree, and you have to okay, let's see like this. If just so Feudal Lords. Alright, you're given a tree. Some tree. The problem is also a bit unclear at first, and the input is just terrible. This has to be fixed. This is some like to the judges critic. Their problems were pretty good on the first input, but this input is just terrible. You can't understand a thing what his wants to say here. I+1, I++1, whatever. If you have to deal with this I+1, do make auxiliary line on the input. So 0, 0, -1, -1, whatever, just not this, because the king who's not Basel to anyone is mobilization type 0, give that in the input. Like, it's much easier to give that in the input, not to deal with questions about this here, this bad input. It's just bad. Okay, I know that you need to make the problem harder, but making the input just this input data like a whole page does not make the problem better, just makes it worse. Okay, this problem is about oops. Okay, this problem is about, okay, you have some x values, it's a constant, which for each constant is just like a percentage, so a divided by b times like 100%. Yeah, times 100%. So like you are given this like you're not given this percentage, you have to find this, and you have to find the maximal x, the largest x, such that this root node, so if, okay, like this, so each lord here, each of these have some like it's a hierarchy of lords, right? So if X% of these lords are mobilized, okay, he can mobilize as well. So it's enough X, it's not enough. It's actually it's a quite misunderstanding problem because it's, yes, it's enough X of the lords to mobilize. Okay, yes, it's at least X of the lords to mobilize. Then this guy becomes mobile, but each guy also takes some time. And then you have to take the maximum of these times from each subtree, and this guy will take the maximum of this time plus the time itself. The maximum time for which it's, how do I explain this? This is not in the statement, it's just you have to figure it out. Maybe I will explain it more on like the code. Okay, so my solution for this problem should not pass the tests. This is one more thing that I don't know if that was intended from the judges, but actually it passes the tests, even though it is not correct. It has a counter example in which my solution will just overflow and don't pass the tests. Okay. So for each, how much time each lord takes, each children take, I push into DFS, then we sort the times, and then we find, okay, for this particular, so we can say if we know X what it is, we know A and B. Okay. If I can get with this equation, I get like, okay, at least this amount of lords and not more than this amount of, and that not more than this amount of lords are mobilized, then we maximize the cost for this subtree. So not we maximize the cost, we say we take the minimum cost for this subtree, for the subtrees to the X value, and then all right, this is a bit hard to explain. And then we need the time needed is just the time for this node. So it's a bit hard to explain. Let me just rewrote once again. So let's just say like this. So at first the king declares mobilization. Those feudal lords who have no vassals of their own begin to mobilize their soldiers immediately. So this tells us that the leaves do begin mobilization immediately. Okay. A feudal lord who has some vassals starts mobilization as soon as at least X% of his direct child start mobilization. As soon as least X%. So how do we know what time will take this X% to mobilize? Okay, it will take the maximum, it will take the time of the largest, if we sort the times of this here, let's say this guy takes time 10 days, this guy takes time 25 days, and this guy takes 50. If I need 2/3 to be mobilized, I need 25 days. I need 25 days for this guy to mobilize and this guy to mobilize. So we take the 2/3, and then we know that this guy will take mobilization after 25 days. So like these guys will take, plus the mobilization that will the time needed that he needs to mobilize, right? So it's just a Depian tree, but the whole idea here is that this X constant, this X is a fraction. And now this becomes a lot harder due to the fact that X is a fraction. We cannot binary search X. Okay, what's the proof that we can even binary search X? Okay, the proof is that if you can mobilize some units, if some X takes T amounts of units, right? And T amounts of time, days or whatever. So like if I say that, okay, if I need 1/3 of my child to be mobilized and it takes 15 days, for 2/3 of the child's mobilized, it will take more or equal than 15 days. Because we maximize the days in each of the nodes, right? Now, if we know that this works, it's a monotonic function, then we have some t limit. This t limit is given on the input, and we say, okay, we cannot do more than 15 days. Okay, the maximum limit, let's say, is 15 days. So we have to find a fraction such that it satisfies that it maximizes the mobilization, but yet it is below the time limit. So it's a bit of a mouthful of words to find this, but it's yes, it's yes, but yeah. What was my yeah, so we actually can binary search over X, but how do we binary search over a fraction, right? My first idea was to fix a value, to fix the denominator to some large value, and then try out like binary search over this large value. But it turns out that it is much harder to do this due to the fact that the answer can be irrational value, like this, 2/3. 2/3 is the optimal answer for this problem, but it is an irrational value. You cannot binary search this unless you know the denominator. So how do we know the denominator? The denominator we know by an LCM. So if we take LCM from, so for each node we have some children, right? Okay, these are, let's say, 5 children. Then for this node I have 3 children. For this node I have 2 children. This node I have 2 children as well. From this node I have 2 children. Okay. So if we want to always divide in some way proportional to the with an integer number of nodes, we can take LCM of this, of this, of this, of this, of this. So we can take LCM of 5, 2, 3, 2. And this is the biggest denominator we can possibly have. But you can see a bit of a problem here. You can see a problem where the LCM might become very large. And believe it or not, they do not have a counterexample for this test. I will now the largest suitable X we're looking for. Let me just read again if they mentioned that somehow the LCM should be small, but no, they do not mention that. Time allowed, no Feudal Lords, direct puzzle. So like with this statement, we say that it is a tree, but they do not mention that the LCM could be is always very low. The LCM of the number of childs for each node. So, in fact, okay, so this, if it's uniform, if all of the tests are uniformly generated at random, it is very low probability that we're gonna have a lot of primes. And the LCM should be relatively small due to the fact that it's a tree, it's uniformly generated. But if it's not, if it's adversarially generated for this exact test, the LCM will become so large that can overflow long with like thousands and thousands of times, right? And weirdly enough, if you take to see my solution, it is exactly what I do. Just I take LCM of how many childs does this node have? -1, because -1. Why make -1? Because this adjacency counts the parent as well. Okay, only the root does not have a parent. Yes, and then we binary search over A. We know what B will be. We binary search over A. We try to satisfy the condition, and we see how much time does it take. And then we search to B+1. The B+1. I thought that if an LCM could be like always in the long range, so this is 10 to the 18th power. This will be just logarithmic search, and that's like 64 times. 64 times search of 64 times simulation, and then we just take GCD. Okay. What is the intended solution? The intended solution is, first we have to find what will be the maximum denominator, and the maximum denominator, it turns out to be the maximum number of the maximum number of children one node can have. Due to the fact that like this fraction should satisfy all nodes. So if it satisfies all nodes, it cannot be larger. The denominator cannot be larger than the maximum number of nodes. But there is a catch here. There is a bit of a catch here. It's still we need LCM. But instead of finding the LCM, we find this maximum denominator. But then you binary search A for this maximum denominator, and then you binary search, then you have like you build a list of candidates of fractions which are from A max to the maximum denominator and A+1 to the divided by the maximum denominator, somewhere in between this. And now this denominator is actually what we're looking for. We do these candidates, these new fractional candidates, and for each fraction we actually compute again. We sort the fractions, and then we actually compute again with binary search which fraction satisfies. And this works in what time it will work? It will work in again logarithmic time times n log n. Why n log n? Because the DFS just goes upwards, and mobilization time is actually what my DFS function does. Source nth element in this, and yeah, I mean, it's fine. It's a fine problem, but it's kind of interesting. Why should this problem pass? Why should this problem even pass with LCM? Why they didn't create these counter tests? Another idea is that you don't often see problems with fractional fractions with like fractional units, and yeah, they use this here structure, which is very handful and like comparing comparing different fractions, and probably there are just like really like even other predicates, even other operations that you can do as well. Like there are always like thousands of operations you can do in fractions, but you don't really want to do that. Like you want to, it just gets a bit more complicated, you know. And yes, this was a weird problem. This was the most weird problem I have encountered yet. It just a bit hard to understand, but it's okay. It's a fine problem. It's fine. So if I would to rate this problem, I would say it's a 3 to 4 out of 10. So this problem was fine. Of course, it's like easy problem. This problem I didn't like. This problem I liked actually. This is fine, but okay, let me translate this because you don't. But this problem, this last one we're going to talk about, actually is not going to be the last one. We're gonna talk about developing loops, but I won't say a lot because I haven't solved this problem, but I won't probably even try to solve this problem due to the fact that it's like more implementational. This Strikethrough is just this is the most interesting problem of the whole round. Congrats to Tomasz Hocevar, who wrote this problem. This is the most interesting of them all. It's a simple problem. It's a problem which requires the knowledge of a certain algorithm, but it's a problem whose solution will make you just understand more about this algorithm if you haven't if you didn't know this algorithm before, right? So what is the problem? The problem is you're given a string of some letters, and then you're given a dictionary, a couple of strings, which you need to find their occurrences and remove. And just like strike out, okay? Their occurrences could match, could be like here, you see this like UPM occurrence here and this Musa occurrence. These two, you will strike out UPM and then you will strike out Musa. Okay, and the only thing that is going to be left after you strike out all of these occurrences is going to be Reshito. This like so this, then this Z is striked out, then R, E, then you strike out a lot of these letters here. Then you come to where's so oh this okay, this is not this is Musa, this is Musa. Okay, so S you have here, so R, E, S, and then this is strikeout, this is strikeout, this probably this, and whatever. It's like this. Okay. You get the point. You have some string, and then say meet go, and then if you have like a dictionary IT and like let's say you have like this, then like let's say you have this in the dictionary, you strike out this and you strike out this, and then you're left with this. The left out characters should be written. Now the string is very long, it's 1,000,000 characters, and the dictionary is 1,000. So what I suppose a lot of people did is just ran campy on like every one of these here of the dictionary, ran campy 1,000 times, and when you find out the word, where that word is, you have some interval and you strike out that word. Whatever, doesn't matter. But this is of course too slow, because 1,000 times running on 1,000,000 strings, this is way too slow for 2 seconds, and quite a low memory. But it's not quite low, it's fine. Memory is fine. Okay, I have RTE because I didn't set up to 1,000,000 here, but whatever. Okay, what is the solution? I will just do just like get the solution here, so you can probably. Okay. So the solution is to modify the Ahu-Korasic tree, try or whatever, to modify it in order to. So Ahu-Korasic initially counts the occurrences of some substring inside of a string, right? And it can do this quite quickly due to the fact that Ahu-Korasic is a try in which like you go down, and then when you fail somewhere, you have a fail link where if you fail in some search, the automaton machine, the whole structure of the graph in of one operation resets you to a very possible other match, to another match. Okay, so this implementation from the Ahu-Korasic for Ahu-Korasic is very simple, very short, and everything you need to know is, okay, here we're building the try. So here we are inserting new node for, so we're going for all of the strings in the dictionary. So this is the size of the dictionary, and for every string we are going down the Ahu-Korasic. If that node doesn't exist, we build it, okay, and then we set it to that's the current node, so it's just like a pointer to the current node. And then when we finish this, when we finish all of these builds on the try, so the try looks like this. So let's say you have the words so you have like this. Okay, you build this, then you have the word ABA. Let's see. Then you build this. Okay, you have this try. You're building this try, and then on the when you finish, you want this state. You want to remember this state. You want to remember some information about this state. If you have reached this match, what should I output? Okay. Now this is where it comes very, very important to change and to modify the tree. We store the size of the string. Why would you store the size of the string? Okay, so what is our idea? Our idea is that when we're given a string, for each of the let's say for each of the words in the dictionary, then like let's see this, and Our idea is this. For each of the letters here, in not in the dictionary, but in the main string. For each of the letters in the main string, we want to find the longest occurrence that ends in that letter. So, for example, if I have like, let's say Connie we have, okay? So, and we have Oni, let's say. Yeah, we have Connie and Oni. So, okay, you have this match and you have this match. These two matches, okay? You have, so you have K, O, N, I is one match and O, N, I is another match, okay? But if I ask you for the I here, for what is the longest match that ends here, you will need to tell me that this is the longest match that ends here. Why? Why I don't need the shortest match? Because I want in O of N then later to sort these matches in intervals and to see where they what is left out, okay? But to do this, we only care about the longest match ending at some position I, okay? That's why I saved this for some information here. When this string is done, I save the size, okay? Then this is just this is for the BFS. It's not like this. And then what BFS does on the Aho try is, first of all, it calculates fail states. Okay. It calculates fail functions for every state of the try. So for every node inside the try, it calculates, okay, if I'm here and I failed, where should I go? Do I go to the root? Do I go to some other match that is possible? Where do I go here? This is the failings. But also it is very important for this state here to maximize the current state and the out of the fail state. Why is this important? Because if I match some state, I want to maximize the length that I return. If you don't know about this data structure, you can take a look at probably or Wikipedia or some other place, I don't know, probably on YouTube, some more depth explanation, but this is very nice implementation of the structure. Everything is done on like arrays, which are very fast. Yeah, you just do a BFS. And now the thing that you need to implement here is just, okay, you have some state, you have some events. These events are the thing, what I said, what is the longest match that ends at that index, and this I call is one event. So there are at most O of N events, because for each index I just want the longest match ending there, okay? I have some answer array. This answer array is totally unnecessary because I can output here the answer, but whatever, doesn't matter. I go through each of the text, I try to match on the state, and then if the out of the state is not zero, if the match is not zero, then I want to push. If there is some kind of match, I want to push. What I want to push is the, okay, ID is just like the character right now minus whatever like match, how long this match is, plus 1. Why? Because if I'm here and I found a match in 4 characters, I want to point out to this character. So let's say that this is 1, 0, 2, 3, 4, 5, 6. Now I find a match of 4 at position 6. I want to point out to position 3. So I will do 6 minus 4 plus 1 equals 3. So I have an event from 3 to 6. So the event looks from 3 to 6. Okay. And I store all of these events. Now I just sort them. So the complexity is of n log n now, because I sort them the events. Then I go just like a pointer technique for each character in what event it is. If it just shift event, and if this character is not in some kind of event, is not in the interval in some event, then we push this character to the answer array, and then we see out the answer. Yes, if it's not in some match, then we want to see to print it out. That's the whole solution. N log n, but because yeah, it works. It's very, very fast. The Ahu Jurassic try is very fast. It's the complexity is of n plus the size of the whole dictionary. So like 2 million or something operations, but it's fast enough. The memory is quite a lot, because I reserved the memory for like a lot. I just put max n for like everything. I reserve a lot of memory, and now the memory just jumps out to like 130 megabytes, even though I don't need 130 megabytes in each test case. Probably vectors will be fine. The time that it takes is quite low. Given that the algorithm is matches and then sorts and all this stuff. Yeah, but that's in quite frankly, that's the best problem in a long time I've seen from like this type of ACM. Quite an interesting problem. Okay. The last problem. The last problem is, of course, when you take a look at this, it's like just, yeah, I'm not gonna really try, like, if I don't need, like, this problem is just, okay, you are given some valid code, first of all, some valid Python code. No, it's not valid Python code. It's some valid code on this. Yeah, it's a valid Python code. Let me just translate. You're given a valid Python code for which this grammar is okay. For which this is the grammar. And what we want to do is we just go, instead of having like for loops, we want to interpret the for loops, but not to evaluate them, but to change the function, to change the variables inside the functions and inside the other for loops. So if we take a look, and another idea is to that the if statements, some statements which are just like the if statements are printed out, then some so some statements like this are also printed out. Yeah, like this is also printed. I don't know why here. Okay, here this for loop doesn't do anything, so we just print pass. because from 7 to 7 and increment 1, this doesn't do anything. And there are these, yeah. So what is to see about this problem is that it's not a straightforward tokenizer and parser problem. If it was a tokenizer and a parser problem, you would just do a tokenizer. You would send these tokens to some kind of parser, and it will build a tree structure or whatever a tree structure, and then you will evaluate this tree structure, or you will do some other things. You certainly can solve it like this, but that's why this problem should take you a lot of time to solve, right? But there are a lot of things that make this problem easier, and the fact that you do not need to evaluate expressions, fact that you only care about like for loops, you only care about changing variable names. And I wasn't sure that like I thought that like, okay, the input could have like some kind of, it will be very hard to change variable names if the input is very malicious. In fact, that like it doesn't don't have like spaces and other like delimiters here between variable names, and like you could have thousands of edge cases for which it won't work if you don't have a proper parser, if you don't have a proper tokenizer for this. Okay, so yeah, I haven't even tried to solve this. This grammar should be properly done and expressed in a acyclic syntax tree, right? But yes, but some people, a team at our university solved this problem with 15 lines of code or something like this, maybe 20 lines of code in Python, with just cruel logic of just replacing recursive things. I know like it's not that bad maybe to write it, but it will certainly have some edge cases, and you should certainly be a bit more cautious about a problem like this. And yeah, it's fine problem, but because there can be a lot of wrong answers, a lot of edge cases for which a solution may not work, it's quite a hard problem. It will take you quite a long time. Maybe it will have to be better, like if it's like some kind of a real syntax tree, real syntax problem, but with like less grammar. Uh, but yeah, I don't know. Okay, there will be, there is some other things here in consideration that may help you solve this problem without a lot of edge cases. It all in all, it shows that the judges didn't want to make it a really hard contest. They had some kind of difficulty in mind, certainly. And I hope to see even better problems, even though these problems were not actually that bad. These were okay problems, good problems. I hope to see even better problems in the future for yeah, for this. So if you have any questions, doubts, if you want to try out some problems, you can always do. You can always try. You can always try them in the link description in the link in the description below. Yeah, that's pretty much it. I'm not going to make it a longer video than this, and I will see you after the second round with a new post contest analysis.